Swayam Prabha. Digital India. Educated India.
Okay. Morning, everybody. How's everybody? Good? Waiting. A little more smile on your faces because 9th day and tomorrow will be bright. Abba, finally it's all over. It's okay to let go. That's good. You should never hold on. Okay, so today's topic, well, we're not doing much of fire. I don't know if we can even erase that part. No, I can't erase what is already there. So we're not doing much of fire. So we're doing a little bit of impact. We've seen one presentation, and we'll have we'll do a little bit more in terms of presentations. But today we'll address a very different topic, but a very relevant topic in the blast design field, especially the design field, because a lot of engineers and a lot of times you may not want to do any blast resistant design of buildings per se. So in those cases you can do something simpler, regular structural analysis, and come up with what is known as progressive collapse. And as the term progressive collapse, it means that a structure is progressively collapsing due to the failure of one element. So what we have seen again so far is we have seen a blast specific design. So this is threat dependent. The threat was defined, and we'll post this. The threat was defined in kilograms and the standoff distance, and we've seen a variety of ways to address design aspects of it. Now, when we look at progressive collapse, the first thing to keep in mind is it is threat independent. Another thing to keep in mind is it is not a blast resistant design. Now, another thing with blast specific design is this is typically element based. You don't consider the whole structure. You're designing, when I say element, you're designing a beam or a roof. We've seen all of this, column. We haven't seen a slab, but a slab can also be designed for slab. Also, we have sort of seen the walls is a slab basically. So all of these are element based, and you're protecting. So when you're designing, you have to decide what to protect and protect it, and then keep adding on to it. But here, when you come in contrast to, this is a whole structure based protection. So this is an element based design, whereas this is in contrast. Here if you see, it's a whole structure. So the entire building is considered. And of course, you do protect, or you don't say protect, I mean we don't call it protect, you do enhance or you add elements of reinforcement and other such things, but mostly it is your regular structural analysis and design. So today we will look at, and you can do a lot of it mainly for concrete structures. So, today we will look at concrete structure design. Again, a lot of development needs to be done further. Even in steel you can apply these elements, but of course in a different manner. What we will discuss today is primarily for concrete elements. So, I will start with the history and definitions. So, for progressive collapse, as we know, this results in significant, if not the entire building damage. We'll talk about design criteria, we'll talk a little bit about the history, then there are some definitions that we will look at. Then if you look at the design criteria, there are two of them, two design criteria that is based on, this is in the US. GSA is this is for government, basically think of it as government buildings, all structures that the government has, and this is for, both of them are available. We will see certain provisions regarding these two. And there are two different methodologies. The tie force method, let us just abbreviate it TF for now, and an alternate path method. So, this is, we will call it APM. So, the APM method requires several structural analyses of the same building with what we call as column or element removal conditions. We remove certain elements and allow the load to be flowing from one path to another. For example, if you have a building like this and you are doing a normal structural analysis, so we know that as you have a load path, this will go down this way, and down. Then in the APM, we might consider several scenarios. Let us say the outer column gets removed or the central column gets removed. So, here these would be two different scenarios you would consider, and we know now the load path is, these are the alternate load paths. It's a fairly simple idea. The only thing is, if the structure gets complex, then you have to go through multiple load paths, and typically this is applicable, all these are applicable for regular structures, for usual structures, and for, you can apply for unusual structures, but you might have to develop, for example, different shaped structures. If you are looking at public buildings such as a big stadium where people are gathered and there is an event, an incident that occurs, so you can apply it, but you have to with the engineer's best judgment. Judgment for APM criteria. So, a little bit of the history, and it is actually very recent. If you see the whole thing this is a timeline from 1960 to 2000. The first one, if you, as we see, the events are what guide the design development. So this was an apartment building. So not even, it's about what 58 years or 56 years old, and so the Ronan Point collapse, as they said, we'll look at some images. That was the first starting point. If you're looking at in 1970 in United Kingdom, this was in Scotland or Ireland, Scotland or somewhere there. Then there was another plaza collapse, which was primarily due to progressive collapse. So that led to, this is in the US. So this is UK, and in 72 it was in the US. It shows different timelines for different countries. Then NBC Canada in 1975, and then in 76 PCI, this is a US based organization, committee. So this is US based. So this is a precast industry. Progressive collapse is common more in precast industry. I don't know about here, but there even now parking garages, multi-story parking garages, it's all precast elements. So it's like assembling Legos. Columns come in, they'll put the columns in beams, they'll place the beams, get double T beams, and then L beams, double T beams, all of them are precast, brought in place and literally assembled. So any failure, connections especially, starts failing, the whole thing collapsed like a pack of cards. So PCI got into this quite early on, so that a lot of it is also based on industry survival. And in 1989, ACI 318, which is our US structural code for concrete design, just like IS 456, this is similar to IS 456, and they had some structural integrity provisions, but it was quite minimal. So the sentence, the wording says, basically saying the structure should be protected, it should be integral. Then in 1999, the Department of Defense got in. This is what is known as anti-terrorism protection standards. Then the government buildings again in 2000, because of further attacks on marine barracks or other public locations. This is a governmental, as I mentioned, this is about 3 hours or 5 hours from where I live. So in this city, this was a huge event at that time. So that led to government buildings protections in 2000. So that's hardly 24 years ago. And there are other developments which led finally to what is now available 2004 UFC. We'll talk about that also. So this tells you a little bit of the timelines. So the images are pretty poor because of the import, but you see this was essentially a gas explosion in a kitchen somewhere here. So this was a kitchen on the outer part of the building, and on the 18th story, the wall panel blew out, causing the loss of supports. So it was all supported one on top of each other, and debris from the upper floors caused each floor to collapse. And here it tells you what that event led to, different things that we just talked about. Then progressive collapse history, some more. This was again a marine barracks, this was in a DOD facility, and this, you see that people do use fairly heavy amounts of TNT, 12,000 pounds of TNT. That's almost what, 5,000 kilograms of TNT. And so there were no changes made, but you see the entire collapse. It's a nice beautiful building that was not designed for progressive collapse, nothing but rubble at the end of it. Then the other next one was, this is the building I said that is close to where I live in Oklahoma City. A significant amount of TNT. This was basically a truck, a pickup truck in the basement garage near one column. Nine-story, and OMRF is, I talked yesterday about different types of moment resisting frames. The response modification factors, you have in concrete and steel, you have ordinary moment resisting frames, you have intermediate and you have special moment resisting frames. So, this is less ductile. The ductility comes in having R as a higher value. So, you have to provide, and that is something that even we have looked at in seismic. And let me just take a little aside. In seismic, R goes from even 1, but typically from 2 to 8, and the R value, this is what is known as the response modification factor. Response reduction factor. Basically what you are doing is something like this. If you have an elastic behavior, if your P versus delta, this is elastic behavior, and this is the, let us say, delta max. Now, if you are designing elastic design, it is the same principle even in seismic. So, this would be the design force. So, this is the design force for elastic behavior, but clearly that is very high. Then you can instead consider a system like we talked about, where you are designing for, say, P elastoplastic. So, this is a lower design force which is practical, but you are providing the same amount of ductility, and here the R is nothing but delta elastic divided by delta P elastic. So, R is your P elastic divided by P design. That is the concept out here, and we are also doing the same thing in blast. We are also doing exactly the same thing. But we are now considering it in terms of delta. This is Y max, Y elastic, and then our mu is Y max by Y elastic. In a way, you can try extending this out. So, it is a similar ratio that we are talking about. So, when seismic you see 2 to 8 and we are getting 22 even higher values. In fact, there is moment you see high mu values, we haven't talked about it or we haven't addressed it in any way. But if you see high mu values, which means that you have to take a lot of steps to ensure ductility, especially if it is concrete structures or steel structures. Connections should be ductile. There is a lot of development length considerations. You can't have brittle concrete. Concrete should have certain amount of ductility to it. There's a few things I'll maybe mention later on. So, the problem here was it had a transfer girder. So, somewhere here perhaps there is maybe here, because you want a lower level, you want to have a open area. So, you have a transfer girder, maybe something like this, and then the upper floors were perhaps, I am just giving you a scenario. So, here the frame goes on in this manner, but this is your transfer girder. So, I think he was smart enough to figure out and take out a column somewhere here. If this goes, you can imagine the whole scenario collapsing. So, the loss of 3 columns resulted in the destruction of roughly half of the occupiable space. And fatalities were not due to the blast event itself, but from the subsequent actions. Coburg Towers, again you see the amount of TNT here, it is a tremendous amount, 20,000 pounds. I do not know what the distance was. Again, it clearly shows the blowout. Again, it may not be fully progressive collapse, but certain parts of it here, for instance, you can see could be a consequence of progressive collapse, many of it in this region. Now, all this led to even the World Trade Center 9/11 scenario the impact of it removed columns on each face of the tower and an undetermined numbers of interior columns and fireproofing, and of course, this is a combination of fire basically reducing steel's capacity and elastic modulus, these things have to be running for hours, fires unchecked for hours until the structure failed. This is another building again for 9/11. Across the towers, debris from the collapsing, I mean yesterday there were some discussions on how to protect against such closed-in explosions. These are some considerations that you should have, is how does the debris affect other structures and progressive collapse to be adopted. In case of walls, for example, you will not have progressive collapse, but if you have adjacent buildings, maybe you could consider progressive collapse in such scenarios. Basically your question. That is an alternative design. If you do not consider protective design, you can just consider alternative design for progressive collapse, and that way at least the structures are protected. Some of the good what you call learnings were in Pentagon. It was limited, collapse was limited. It had a lot of redundant and alternative load paths for beam and girder system. There is also short spans between columns, and there is a lot of continuity. All these have been adopted throughout the supports. We will see later on providing, and it was also designed excessively in excess of what the service live load was. So, residual load capacity significant. Again, some of you are working on the remaining load capacity. This had significant residual load capacity and it also had spiral reinforcement. All these are recommendations, not recommendations, it should be requirements. For columns, spiral reinforcements provides a lot of integrity and the ability to external walls again as transfer girders. This allows for APM. So, what are the different progressive collapse guidelines? One is the UFC 4- you can download this 4-023-03. So, this was published in 2005 and there is a whole lot of different updates to it. I am sure there are other updates as well now. And of course, the first document that we talked about. This is the day 1 document. And this defines the levels of protection. But primarily, this is the main document for progressive collapse. We'll take aspects. If you look up other guidelines, the design guidelines may be different, recommendations may be different. So, what is the purpose and scope of all this of progressive collapse? This is it provides design requirements that are necessary to reduce the potential of progressive collapse, primarily for new. In existing, it may be a challenge. How do you need to, if you are doing mitigation, if you are involved with companies that say mitigation work, how to reinforce the structure. The task is, I have the structure, how do I reinforce it? You can use progressive collapse analysis in order to suggest recommend additions to it. Now, this is again unforeseeable event, then incorporates, you have to use your own judgment, effective and uniform. The thing is, you have to provide a uniform resistance to progressive collapse without expensive or radical changes to typical design practice. Applicability is for, as I said, also you can add usual or regular structures to it. Although if it is unusual structure, then you have to decide on where the column removal criteria should be. Now, ASCE 7, which is the SCI, is nothing but the Structural Engineering Institute. So, ASCE 7 has certain guidelines. It's very minimal. All it says, this is in 10. I don't think the updates have a whole lot any different. It just says the spread of an initial local failure from element to element. It defines what progressive collapse is. And progressive collapse is still not quite directly addressed in US codes because it is a specialized event, and there are other public buildings you normally may not. It is because it is going to be a little more expensive. So, you are already limited in your budget, and you are suggesting progressive collapse as a designer, as your company, you may lose the contract itself, although you think it is needed. So, that is why US codes, people have not spent time putting it where, because there are existing frameworks for government buildings and Department of Defense buildings. So, the general structural integrity, it says buildings and other structures shall be designed to sustain local damage within the structural system as a whole, with the structural system as a whole remaining stable. So, which means a column can fail, but not the building, and not being damaged to an extent disproportionate to the original local damage. So, in other words, if you have a column failure, let us say this column failure, and this is the column that is failed, it does not mean that you are going to have a displacement that is so high that it will still tend to disfigure and collapse the entire. You would still design to keep the structural integrity so that of the rest of the systems, because an extension here will start collapsing other. So, you are not preventing. So, you are not preventing the collapse itself. So, this is designed for normal operations. We call it serviceability here. To continue after you definitely will require repairs, but the structure integrity is still maintained. So, there are two approaches. One is a direct design approach and the second is an indirect design approach. You can have certain we'll have a little bit more about it. So, the direct design approach shall be achieved through the arrangement of structural elements that provide stability to the entire structural system by transferring loads from any locally damaged region to adjacent regions capable of resisting the load without collapse. So, that is what is direct design definition, and indirect design is you provide. So, this is strength based, direct design is strength based, whereas indirect design is detailing based. So, this is strength of the primary elements. Whereas detailing is you are detailing existing elements or existing slabs, columns, etc., or maybe with some additional reinforcement that is not designed. So, designed for let me say just specified loads. You are not analysis based, structural analysis based. Other detailing aspects providing sufficient continuity, for instance in progressive collapse, if this is your beam column junction, you will require the reinforcement to be continuous. So, this is continuous reinforcement. And redundancy, energy dissipating capacity, ductility, this is especially at beam column junctions. And we have in seismic what is known as the weak beam, strong column approach. So, if you have a plastic hinge formation, if say this is your column and a beam, you will design such that the hinge forms in the beam. The plastic hinge forms. Over design your columns under. So, you over design the columns. It's okay, na? Huh? It's okay, right? It's come back? Okay. So, you over design your columns, under design your beams. So, the hinge formation occurs within the beam itself. Now, coming to direct design, the explicit consideration of resistance to PC by two different approaches, alternate path method, and then added local resistance by specific local SLR method that requires parts of the building. So, this is where your threat based design comes in, based on W and R. you can design certain elements, not all, but you can design parts of that structure to resist a threat, and the rest of it you are using alternate path method. Any questions again so far? Essentially, this ensures no critical, to prevent localized failure. Continuing, I think this is, I don't know if it's the same thing. Okay, continuing on direct design. Okay, so we've talked about this to provide sufficient strength from accidents or misuse. So we've talked about the SLR and the alternate path method. So the alternate path method is threat independent. So there is no R and W involved in this case. Structure must bridge over a missing vertical load bearing element. When they talk of immaculate removal, that's the term used. What it means is, you have a building, and if this is your column, let me add the beam here. So if you have a column, so the failure is here, not within the beam itself, because if it is within the beam itself, again through some of the detailing, even in steel you can do detailing in a way that the failure occurs within the column, and how to address that, those are some things you have to look into. We are not going to be looking into it today, but so this is what is immaculate removal. So failure at the column, so a failure in the column rather than the beam, so that the beam continues, integrity of the beam is maintained. Structural response mode is considered flexural, so then you have the beam bending this way. And alternative is to employ truss virindle action or large roof line beam spandrels from which lower levels are hung. So in this case, if there is sort of a building like this, you are sort of hanging the lower levels. You can even consider action like this, where the lower levels, the load path is going this way, the load path. So here you are pulling down, basically hanging structure. And this is also not uncommon in regular structures. If we have museums and other such things, for example, they will, I've seen this in a museum where moisture prevention, to prevent the moisture from getting from outside and inside, they actually send the load path up and out through the system. I don't know the details, but it's not uncommon, and it's not just used in these types of applications. As we talked about, the specific local resistance is threat dependent, and load bearing elements must withstand. This is the threat design. And you can employ all the methods that we have been talking about so far. Now ASCE 710 It considers indirect design, implicit consideration of resistance to progressive collapse during the design process through provisions of minimum levels of strength. We will see here what we will call as demand capacity ratio, and continuity and ductility. So, ductility is again ensuring, for example, you use steel. If you are using steel, this is F sub u and F sub y and F sub u. At least 25% increase, and you can have limits on how much extra ductility should be provided. So, those kinds of steels should be used. Using high strength concrete without fiber reinforcement could be an issue. High strength concrete tends to be less ductile. So, often under normal concreting conditions, your Fc prime or Fck is restricted to being less than 10 ksi. In other words, if you are using things like self-compacting concrete, look into the stress strain properties and ensure there is ductility. Then ASCE in 10 years ago, this is in 2014, the concrete code. It started with detailing requirements to improve redundancy and ductility, and of course now we have 31822 which is updated, but just as a historical perspective, 318 in 2014 underwent a major change, overhaul. It is more in terms of reorganizing the code rather than the code itself changing, sort of mirroring the steel design codes. So, that is where things, that is when things got improved. So, what are some of the strategies to improve structural integrity? This is what we said: good plan layout is usual structures, no recess or reducing recess locations, re-entrant corners, all those things. The integrated system of ties, we will take up a problem on tie forces, returns on walls, then changing span directions in floor slabs. So, for example, if you have a slab, then the span, if let us say this is your slab and you design your, basically what you are saying here is, if this is the design span, if you lose the support here, so you lose loss of support, so if you have the loss of this support, you are going from spanning to span this way, span direction changes. So, having provisions to provide for reinforcement. Then load bearing interior partitions, catenary action of floor slabs. We could do this in terms of some tie forces. You can't really calculate the catenary forces coming in a slab. Even in your structural analysis, that is a challenge to do, but by tying the slab up together in a nice way, having ties here, say these are ties, and then if you have an opening, providing ties around the openings, all these are ties. They all enhance, even providing internal ties, all those we'll talk a little bit about that. beam action of walls, the shear walls, and then redundant structural systems, ductile detailing, additional reinforcement for blast and load reversal, and compartmentalized. So, breaking the frames up into different compartments, so having a gap between those. So, these are all different strategies that can be adopted. So, the alternate load path, this is what we talked about. Usually this is your negative moment region, but in the alternate load path that becomes a positive moment region, and what the reinforcement shown is your normal reinforcement. So, providing for continuity here is a simple step that can be taken due to the loss of this primary support. Other thing is providing, we talked about this, providing continuous reinforcement across the connection is essential for, this is a, I do not know if you can read it, this is a double span condition. It does mean excessive congestion of reinforcement at the junction, no doubt about that. So, but that is part of what you are doing here. Steel connections, these are hard to read. A lot of seismic failures occurred because of welding, the types of welding, types of connection that changed a lot of connection detailing and moment. There are, let me mention, seismic research has developed very advanced ductile connections. So, look into that in case you are looking for adequate. For example, if you say theta equal to 10 degrees, this is a large, very large rotation. Even theta equal to 2 degrees can be a significant deflection response, especially if you see a span of 30 feet, 40 feet, 2 degrees can also result in significant number of inches of deflection. In steel design, we know that a lot of providing shear resistance, this is what is known as a panel zone. I am not going to get into it. When you are designing a moment connection, you are going to be designing for these stiffeners, and then you are also going to be designing for shear in this panel. So, making sure the integrity of the panel is maintained by either increasing the providing doubler plates, increasing the thickness. Typically, you do not go for, you can, if you can increase the thickness of the web without adding doubler plates, it is better, but doubler plates helps to locally increase panel zone. So, those conditions must be looked into for, that is what it says, a weak panel zone. So, having a strong connection here, and again you are providing plates out here, essentially you see the plastic hinge is formed. So, this is or the damage is in this region, so that this is for immaculate column removal, it tends to fail out there. What is a plastic hinge? Okay. So, question is, what is a plastic hinge? And say you have a fixed structure, right? So, this is fixed, and you have done, if you fix and, so you will have a negative moment here, M1, M2 and M3, negative, let us say M1, whatever be the loading that you apply. Now, what happens is, in steel, even in concrete, and we have done in the blast design also, that you have RM and you are designing for certain ductility, correct? So when M1 becomes equal to some Rn, some constant multiplied by Rn, right? Then your structure is here, and then the structure can rotate. So structure, you say it's not, doesn't exactly suddenly becomes a rotational hinge, but it rotates structurally or structure free to rotate without loss of capacity. So that is what we call as a plastic hinge. So you say that when your M1 equal to C1 Rn, a hinge is formed. And similarly, another hinge would be formed here. Then when M2 becomes equal to Rn, then you have a third hinge formation. So you have a hinge here, a hinge here, and hinge here, and the structure will now behave like a rigid structure. So this is what is called as a mechanism. This is a collapse mechanism. So a plastic hinge, in other words, it's not a real hinge. A real hinge would be in a structure. This would be a real hinge. If you've seen under bridges, you'll see nice big rods out there, and you actually see hinges being designed. But a plastic hinge is in a fixed connection. When the capacity reaches and it has sufficient ductility, then it's free to rotate. That's what is called as a plastic hinge. So tie forces is what we will be looking at. It's purely tensile. Goal is to hold the structure together, and members must be able to transfer loads from damaged part back to the intact portion, and a significant damage can occur locally. Members and connections must be able to undergo significant displacements and rotations. Now, alternate path method and local resistance I have talked about. Basically in alternate path method, oh, what happened? Oh, I think. Okay, I have to be careful out here. Okay, so the alternate path method essentially has two scenarios under normal circumstances. We are looking at a central column removal, edge column, this is the corner column, and the edge column in the lower floor primarily or one upper floor. So, and then you do perform multiple analysis, and then we will consider what is known as the demand capacity ratio. So the tie forces, they act in this manner. It allows, this is the way we allow for catenary action. Collapse is resisted through tensile forces, and you will see that we are going to be designing for tensile forces in the slab. Then the risk categories, this is basically, you can say, for very low level of protection. This is there's another UFC that defines, but these correspond to different levels of protection, but it's not exactly equivalent. You can think of it. So as you see the occupancy category increases, the tie options exist. You have here tie forces and enhanced local resistance or APM. So you don't need to remember it, but guidelines are provided, and as the occupancy category increases, you are required to do both. Now if you see the final, all the national facilities, any strategic, and everything is tie forces, APM, EL, and especially for the first and second story. So this way you need guidelines. Engineers need to have some starting points. These are the starting points for different types of occupancy categories. You can use strength reduction factors in this case, because in blast design we set strength reduction factor as 1, but here you want to prevent failure. So phi is less than, this is your, for example, you calculate Mn, the actual resistance, I do not know what term is used here, the actual resistance is phi. We have calculated Mn yesterday, day before, so the resistance factor is less than, this is the resistance factor. Then modeling parameters, acceptance criteria are there. ASCE 41 is again, a lot of, as we have mentioned several times, seismic rehabilitation is a basic guide, and that is the main reason. Now the main differences between blast and seismic, seismic is, it works by collapsing the entire structure, whereas of course it does start with localized damage, but the entire structure is acting, experiences, this entire structure experiences the seismic event. But here the localized element first experiences, element feels the extent or the largest extent of the blast event, and then of course it does progress. So the response is still localized. Seismic is horizontal and temporary. PC, progressive collapse, is vertical and permanent. The damage is again in seismic throughout the structure. Here it is local initially, and the goal is to keep. So basically design wise you are going to focus on the entire structure here, but here is to prevent from spreading across. The differences is seismic is cyclic and no axial loading, here 1/2 and there is 1/2 cycle and there is significant, and here this is also impact. So you can have impact factors, you can add impact factors such as you have seen the dynamic impact. So impact factors in bridge design, for example, you calculate the impact factor. In calculating several even live load factors and others, we add to calculate the resistance, available capacity, impact factors come into play, similar to that. Here best practice recommendations, this is the for concrete special moment resisting frames, and then for structural steel also similar things, wood, there are some, there are a lot of, wood has a lot of factors, this is a time effect factor, that's own, wood has about 8 to 12 factors, I do not know, I have lost count of it, but there is significant amount of factors that affect wood, this is just one of them. So here is what we will focus on when we, and we will do a problem later on here. Internal loading and transverse ties. So this is, these are the types of ties. The first one is internal ties. ties are nothing but reinforcement. So, ties are reinforcement in slabs and columns. We will see that we try to avoid adding reinforcement to the beams itself, because that affects the beam behavior. If you are designing a beam for ductility and you provide additional tie reinforcement within beams, that will reduce the ductility of beams. Now it is making it doubly reinforced. So, we will look into that. So, the dotted lines tells you internal ties, and so this is longitudinal, two types, longitudinal and transverse types. Again, ties, let me emphasize, for catenary action of slabs. That is the main. So, there is no calculated design force, there is for prescribed design forces. So, there are two types of forces in design: calculated, where you go through an analysis and get a force. Otherwise, for example, lateral bracings, there is no calculated force. You have a prescribed design force as so much percentage of the load. So, that is what. So, when you say prescribed, maybe as a percentage of the applied loading. Then you have external ties, peripheral ties. So, the second type is peripheral ties. As you see, the peripheral ties, these are the dashed lines here, and then vertical ties in columns. I think we should have time today to go through an example in this one. Let me quickly assess and make sure. I would like to get to the problem in the second part of our lecture. Okay. The requirements are considered in addition. So, separately is you do your normal analysis, design of, even in design you go through enhanced design, in addition, let us say, to the APM design of members such as beams and columns. So, in addition, then you go and add additional reinforcement, ensures that tie strength is greater than tie force with no other loads acting, no minimum strength or stiffness for anchoring members. But if you provide reinforcement, say this is your slab and you are providing a tie reinforcement, the tie reinforcement does come into, you have to anchor it well. So, you can't just leave it hanging here. So, the anchoring, so that if a tie force, the tie force is here, there are, and you can use your normal hook designs or hook provisions for this purpose. Tie forces, continuous load path that is geometrically straight. So, if you see these are members, the inner removal of a column, this just illustrates. So, what it says is anchoring internal ties. I think I went here, these are seismic hooks. Hooks for normal design versus seismic designs are different. So, here you provide adequately anchored peripheral ties at any interruption So if you have holes or if you have openings in the slabs, then you provide ties, anchor internal ties to peripheral ties with seismic hooks. So essentially, if you have ties going this way, so this is a peripheral tie and this is an internal tie. So that's why, and this is a peripheral tie. So here you'll have a beam, or let's say your beam is, and then your internal, these are your peripheral ties. Say this is your internal tie and peripheral tie. Then tie forces must be carried by floor and roof systems. Unless structural members and connections are adequate with 0.2 to 11.3 degree rotations, that is a significantly high rotation. So for most systems you do provide acceptable systems, let us not get into it. So the design loads for floors now is considered, this is our normal load combination with one dead load and half live load. Adjust for concentrated loads and various uniform loads. Now add cladding loads. So we will see it in the example for the peripheral and vertical ties. This is in columns and this is in slabs. We add any cladding, basically this is a wall, our external wall. So how do you consider the area? This is your tributary area. So the tributary area you consider, the area must be sufficiently anchored or developed to achieve the required strength. So here if you see sub area with heavy, these are all different types of loading. This is an area with heavy loading, this is an area. So if you have areas with heavy loading, this is a heavy load area, this is a light load area. Then what it says here is you are providing a tie at the periphery here too. So sub area with light, then peripheral ties are based on the heavy floor load, peripheral ties are based on the light floor load, and then you are also providing peripheral tie between the sub areas with strength equal to the sum of the peripheral tie strength from each sub area. You will see how to calculate in the coming slides. Then you have internal ties in both directions, longitudinal ties as well as transverse ties. Again based on, it is basically based on the load that you are carrying here. So if the dead load is heavy, the floor load is heavy, the tie force is higher. Now it is a simple prescribed, as I mentioned earlier, this is a prescribed force, fairly simple calculation. So internal and longitudinal transverse ties, the required strength is in kips or in newtons. Wf is the floor load, tie span length. So if this is your longitudinal and this is transverse, so this is your span length. So LL for longitudinal, LT, say this is LL and this is LT, and 0.5 HW for one way spans. So that's and the maximum spacing between ties, this is for reinforcement. This is maximum, but clearly maximum spacing you would probably provide much lesser than that, 0.2 LT for longitudinal ties and 0.2 LL for transverse ties. Do not worry about the restrictions. Main thing is internal beams, no ties within the width of the slab directly above. It is hard to do the second part of it. This is important. All ties are provided inside of the slab, I mean inside of the beam. So, determination in LL and LT, if you see here, now this is 20 feet, so there are different spans, 20 feet, 30 feet, 20 feet and 20 feet. So, longitudinal direction here, this is 30 feet. So, L1 is 30 feet, spacing less than 0.2 LT. So, this is your LT. So, it's a simple mathematical calculation. Now, here in the transverse direction, okay, this is 20 feet, so that is given out here, same thing. So, then peripheral ties, the force is different, FP is 0.6, it is 6 L1 and LP. Now, peripheral ties are provided within, so this is your, let us say, slab, and let us say you have your beam system within here. So, this is your beam. The peripheral ties are sort of provided in this region. So, peripheral ties come and it says L. So, this here is LP. From here to here, LP is 3 feet. So, location within 3 feet of the edge or the interior face. If you have a perimeter beam, then you provide the ties within 3 feet. Restrictions are no ties within the slab directly above unless there is significant rotational capacity. Again, keep in mind all of this is to get the catenary action. Then the vertical ties required strength is given by maximum of AF 80. This is the floor load on any one story, the column or wall tributary to any one story. Then extended from foundation to roof level. So, when you provide these ties, you are making sure if you have multiple levels, these ties are going all the way. So, extend from the foundation to the roof level. So, this is your roof. So, the ties without any break. If you have a wall, so if you have load bearing walls, then we consider it this way. We will look at an example. Then if you have openings, now you have internal and external ties, they talk a little, there are details about what type of splicing to be provided. Then if you have openings, the openings are also you are providing peripheral ties. So, you have here peripheral ties in opening. Again, anchor is provided, as we said, this is your peripheral tie, you always anchor it to. Anchors, this is a transverse tie, a transverse and longitudinal tie, and this is your peripheral tie. So, anchor them into the peripheral ties. So, again this is a schematic, ties are not allowed in the shaded area. This is a beam, all this area no ties are allowed. Again also on top of here. So, 3 feet or 1 meter, you tend to provide your ties in this region, all peripheral ties in this region. So, if you may have reinforcement like this. So, peripheral ties within 3 feet or 1 meter there. Now, I will not get into it, these are all from seismic principles, how to provide for ductility. This is deformation, a lot of these are ductility requirements, but what I would like to talk about is, maybe I should not present this even. Let me see if I have any notes on some of these. Yeah, most of these are ductility related provisions. Okay, here is where the alternate, yeah. So, remove, this is for alternate path method we had talked about. The different requirements near the middle of each side and the corners. This is removal of elements for alternate path method. Any significant variation in discontinuity and geometry. Underground parking or uncontrolled public areas, you remove elements here also. This is in the first and second floors, but remove elements. So, the affected stories right here, affected stories are first above grade, directly below the roof, mid height, above column splice or change locations. This is really multiple structural analysis. You could end up with dozen structural analyses, especially if you have lots of load combinations, then you have to look for multiple analyses for all of those load combinations in each removal case. So, cost wise it can be pretty significant for the client. So, the column locations are provided with multiple stories here or multiple bays, interior columns recommendations are given. If you have walls, again removal of wall locations, they are all provided. And this is the, what we talked about was the immaculate removal of columns. Preferable is to have the column fail in this manner. In your analysis, of course, you have to consider that in design detailing, it might be a challenge to, but your structure is going to likely fail here. So, you have to detail in a manner that the column will fail below or will get damaged below the beam. Analysis procedures, you can use your regular linear static, applied full load at one time to structure with VL with the element, this is the element removal. Again, these are recommendations, we are not getting into it, but you can look if needed, you can have that. So, the load combinations in our static analysis, we normally have base immediately and adjacent to above the removed element. Instead of here 0.9, this is one of the load these are ASCE 7 load combinations. So, the load combinations, this is basically for uplift conditions. The GSA, it's simplified 2 times dead load plus 0.25 live loads, but the UFC has these with 0.5 live loads, here it is 0.25, but GSA says this is for your impact factor. Yeah. Yeah, some of these also. So, we have these, usually our ASCE combinations, the 0.9 comes with, this is 0.5 live and 0.2 S, then there is also earthquake combinations that come in. So, instead of what they are saying is take out that 0.9 and replace it with 1.2. We'll skip some of these again, as we are not going to do an analysis. I think I should really work a way to, okay. What I want to talk about is the DCRs. So, this is what is called, once you do an analysis, you do what is known as a demand capacity ratio, demand to capacity ratio, or DCRs. I'll define a DCR in a moment. There are no restrictions on regular structures, but must be less than. So, this is a DCR is, let us say, QUD, which is the load from the APM analysis of a member. This is member by member. So, this is the load from the analysis of the member divided by, let us say, QCE. This is the capacity of the member. So, the criteria that is used is DCR should be less than or equal to 2.0 for all members. So, as you can see, there is a lot of post processing involved. You calculate several scenarios of load paths, and for each type of load path for each member, you are doing analyses, you are calculating the DCRs. So, it's a lot of work, but addresses the whole building as such, and you are not limited to, you are not designing every member for blast resistance. So, this tells you recommendations on applying the member, apply the loads, second order P delta analysis, and then compare. A lot of these are ASCE 41 criteria. So, the book you can download, there's an entire book by the GSA, I do not know if it is available for downloads or purchase, for alternate path analysis and design guidelines. For these are primarily for companies that are doing business with the government there. Again, it's a public distribution, distribution unlimited, it says. So DoD, what we talked about was DoD. This is for the GSA. These are all the different provisions. Again, I don't think I'm doing any justice by